Hello, everybody. Um, Today, oh, look, my dog. Yeah, she's cute. We are going to solve some equations and systems of equations today. I'm going to basically go through some of the book problems that I've reworked, but we're taking two functions and we're going to combine them in multiple ways, paying attention to how the solutions are different depending on how they're combined. This is three of the ways right here. We're going to talk about graphing two variable inequalities real fast and then go down here to solve them another two ways. So to begin with, we have functions c of x and g of x. I have labeled them all. First off, pretty simple question. How can you use the graph to determine the solutions when they're equal? What are the solutions? Well, if you're using the graph, I have a pretty good idea that you're going to look over here and decide it's these points. Wow, that's an ugly color. Changing that right now. Let's go to something prettier. Here we go. Also not cute. Sorry, I don't know what my issue is. Here and here, right? That is where they are crossing. That makes sense that those are the solutions. However, if we're talking about when a function is equal to a function, if you look down here at if it was an equation, we only have the variable x. So the answer to this question is just when x equals, so when are they equal? It's when x equals, that would be -3 or 2. Algebraically, you can solve this problem. Moving everything over to the left side, you'd have x squared plus x, and then -3 minus 6 is 0. This does factor to x plus 3 times x minus 2, which would also give you the same solutions of -3 or 2. Okay, not a big deal, right? On the graph. When your equation is this, remember this is only in the terms of x, so y is not part of your answer. Just gonna draw some arrows. So what about when one function is in relation to the other, like when one function is less than the other or greater than the other? How do we deal with these? Well, if we're thinking about this, when is c of x less than or equal to g of x? It's kind of like asking the question, when is the line c of x below the line g of x? If you think about this, when is c of x underneath g of x? Well, it would really just be in this section from here to here. And you still actually have the same boundary points. So these aren't actually changing. They're going to be over here as well. Same boundary points. When is c of x below g of x? Or when is that function less than or equal to the other function? Well, it's in this area right here. So that would mean we're talking about when x is anywhere between -3 and +2. And this is actually less than or equal to. On a number line, you would put a solid circle here. You would close your circle here and you would connect, oops, I erased it. You would connect the dots from here to here. And your solution would be this, 2 parts. So when is c of x below? Well, in that section. If you're looking at the next question, when is function c greater than function g? Well, function c is going to be greater than function g on the outsides, out here and out here, right? So function c is higher than g in those sections there. How would these be represented on a number line? Well, we still have the same solution points. They're open circles though, because we're looking at greater than, and this would be on the edges. So c is actually greater, pointing outward. So we would write this one and say x is less than -3 or x is greater than 2. This answer has an or because you can't actually be in both places at the same time. You are one of them or the other one. So when is it above? I'm going to just add that. So algebra, if you solved any of these, you would always end up with the same boundary points. And then the question is, where is this actual zone of answers? So you're not going to get different boundary points. You're just going to have different looking solutions depending on the question. When are the functions equal? When is one above or below? And then we get to actually graphing them with two variables. So that was all in one variable. If we're moving down here to just think about two variable graphing, this is just a really quick reminder of graphing inequalities in two variables. First thing is really graphing the boundary line or the curve. And I'm going to talk a ton about how to graph a line. The second thing would be paying attention to your symbols. And there's a nice handy dandy little section over here to remind you, in general, if they're y equals, then you can usually use this chart here to help you know what way to shade. You can also test points. So you've got solid lines if it's equal to, dotted or dashed lines if it's just greater than or less than, meaning that's a boundary point and not, you can't quite get there. Let's see, I'm just reading the rest of this. Once the boundary's graphed, choose a point that doesn't lie on it to test. So you sort of have two choices. Like you can always test points to decide where to go and where to shade. You can also use this little thing here. If you've got them y equals, it generally is pretty solid about shading above or below. So this is just a super quick checking of testing, like over here. So is 0, 0 part of the solution set? When it says test it, it pretty much just means plug it in. Is 0 less than negative 2/3 times nothing plus 2? So that becomes nothing. So is 0 less than 2? Yes. So 0 is part of the solution, which means you shade the section with 0. So you shade that 0, 0. Sorry. Not just 0. If you're checking the other one, if you try 0, 0 and test that point, like 0, 0 is going to work. 0 is greater than or equal to negative 1. So 0 is part of the solution. If you look at this graph, there's another dot. They checked like to test the point, the 3, 1. What about that one? Well, if you plug that in and try 1 is greater than or equal to 3 squared minus 1. Is 1 bigger than 9 minus 1? Nope. So this is not in the solution set. So as you can see, this 0.31 right here is not in the shaded zone because it doesn't actually make the problem true. So yeah. So all right, now to ours. We can combine these in two ways. On the left side, there's equal signs. It's a system of equations with equal signs. So what's the solution? Well, if we're not solving it with algebra and we're just looking at this, this is 2 points and they are -3, 0 and 2, 15. So when you're solving a system of equations, it's in two variables, so your answers have two variables. These are the actual points, both x and y, because we have both x and y in the problem. What about if we're dealing with a solution to a system of inequalities with these symbols? Well, we need to look at what's happening for each of these. So ideally, if the top one is c of x, we're shading above that line. So if we're thinking about the line of C, right here's C. And we're gonna shade above it or equal to it because it's greater than. If we go back to this thing and we're looking at our symbol right here, it's typically going to be a solid line and shading above. Oops. So we've got this section, right? All of this section is that inequality. If we're looking at g of x, we've got this line here, right? This is g of x here. And we're going to shade above it. So we're shading all this stuff up here, but it's a system of equations. So since it's a system of inequalities, sorry, not equations, we have to solve both of them. So there's sections here that don't actually work, and there's sections that do work. The solution to a system of inequalities is always going to be where the regions overlap. So this is not our complete answer because right now we have sections that are not in, that don't actually solve it, that are shaded. So I'm going to erase a few of these. So if we think about it, we're talking about it being above the purple line and oh, I totally graphed that wrong. Sorry, and below the green line. So if we're thinking about how to graph this, so scratch all that. I don't know how to erase my videos, so sorry. Right, we are going here, purple, above purple, right? Everything above purple. And supposedly, now my bad on that before, everything below green, right? If we're thinking about where's the section of overlap, it's only this little like Nike swoosh that is actually fitting for both of them. So now I'm going to legitimately erase and actually just shade in my answer, which is going to be in this Nike swoosh, because this is the only part that makes them both true. Sorry for the mistake. Okay, real fast refresh of these, right? We've got these two equations. They're combined in multiple ways. If one is equal to the other, we're just looking at the two x values. They are on the graph. They can come from algebra. If you're talking about when is one function above or below the other, then one option is to graph them both and actually look for that zone where the, like for example, like even here we can draw this, like when is it true? Well, right? If we think about it, purple is below green in that section. On the other one, purple is above green in this section, on the outside of the two boundary points. If we're looking for when they're a system of equations and when, what is the solution to the system? Well, it's actually both the x, y coordinates because we have two variables in our equations. And lastly, it's a system of inequalities, so they're graphed and you're looking for the solution that makes them both true. So it's where the regions overlap, which in this case is the Nike swoosh, above purple, below green, above C, below G. Here's another one to try, different type of problem with absolute values. So you've got an inequality. We're going to look at this one over here. And the question is, how many boundary points are there? Well, it's an absolute value inequality, so we should know off the bat that there's going to be 2. Would these be filled circles or unfilled circles? This would be unfilled because they're greater than, right? Greater than, less than is unfilled. If they were filled, they would be equal to. So if we're going to solve and mark some boundary points on a number line, we probably have to solve it. We do need to decide what portion of the number line works. And you can do that by testing a point. So here's our problem to solve. I'm going to first add 2. Not sure why I'm showing my work, all of the work, but this is going to be greater than 8. When we divide both sides by 4, we have the absolute value of, whoops, the absolute value of x plus 1 is greater than 2. Now it will split. So here's an option. You've got x plus 1 is greater than 2, or you have x plus 1 is less than negative 2. Remember, with absolute values, you've got a positive and a negative option that are going to both turn into that number when you take it out of the bars. So with the inequalities, when you do switch the sign, you also change direction. So on this left side, we've got x is greater than 1, because we're taking 1 off. On the right side, we have x is less than, and we're going to have negative 3. So our points are negative 3 and 1. These are open, and now we have to decide what way are we shading. So if I was going to pick a point to test, I would pick 0. 0 is pretty simple to use. If I plug 0 into the original problem, I'm going to test it. I've got 4 times x plus, x is 0. 0 plus 1 minus 2 is greater than 6. Is this going to be true? Well, this is 4 times 1. 4 times 1 is 4. 4 minus 2. Is that greater than 6? Nope. So 0 is not a solution. Meaning we go outward. 0 is not a solution. We don't include it. And this is also true. If we look at these x and our actual equations, x is greater than 1 or x is less than negative 3. I actually got that here in the bottom without even actually having to test a point, because I do know how to switch my signs. You didn't know how to switch your signs, you could just solve it with equal signs and check. Okay, last thing, Bert and Ernie. They were actually working on all these problems, but they decided to do this with a system. So the question is, what system of equations would they graph? Pretty much you're just going to take each side and turn it into a single equation. So the left would be 4 times x plus 1, the absolute value of x plus 1 minus 2. And then the right side, so this would be the left side over here, that would make an equation. If we wanted to take the right side and turn it into an equation, it would just be y is 6. If we graph this, y is 6. That's pretty easy. It's here. It's just a horizontal line at y equals 6. And we know how to graph the absolute value. It's got a vertex of -1, -2, and a slope of 4. So from there, we're going up. Whoops, that's too high. No, it's not. Sorry. And here, and here. And that looks like 4 and 4 there. So I can draw this. I can draw that. And if we look at our graph, we can see that these are the same boundary points right here. That x is -3 and that x is 1. Same thing we have. Now, if we're thinking about using the graph to figure this out, basically it's asking, when is the absolute value above 6. So the question this in words is, when is the absolute value above 6? Well, if we look at that, to answer that question, it's pretty straightforward. It's actually anything on the outsides of this. So our answer matches here from the graph exactly what we did over here. It's when x is smaller than -3 or to when x is greater than 1. I hope that helps. You guys actually have a worksheet to do. I don't have it in my Notability at the moment, but it's very similar. Let me see if I can pause this and put it in and show you. 1 second. Okay, so here's the 2 worksheets that you have. This is what it looks like. It's the 3-2-1 practice worksheet. So it's very similar to what I just did, asking you similar questions about when is one of them greater than or less than. So your goal is to pay attention to how to write your answers. It's not very much about solving with algebra because it's all on the graph. So it's about how does your answer look based on the way you are combining the equations. On the second page of this one, you're going to graph 2 and answer some of the same questions. I'm sorry there's not a lot of space to write your answers, but they're the same type of questions as up here. On the other worksheet, it's actually just some practice with inequalities. So graphing a few linear inequalities, some quadratic ones, and then down here there's some systems. It looks like they're mostly quadratic, linear, or absolute value. Oh, sorry, that's it for now. I hope this is enough to help, and you can always email me with questions.